Okay, in this video, we're going to analyze and graph all 6 trig functions. And we're going to start with graphing sine and cosine. And so, working our way here, we're going to work on this problem on the left-hand side. And at the very top of this page, I have the general forms for cosine and sine, talking about what all the constants represent. The domain of sine, remember, is going to be the set of all real numbers. Now, to find the range of sine or cosine, I have to determine the midline and the amplitude. The amplitude is the number that multiplies to the front of the trig function, and amplitude is always positive. So the amplitude here is 3. Midline is the number that adds and subtracts on the end of the trig function, sine or cosine. And so our midline is 1. That's going to allow us to find our true maximum y value, which is the midline plus the amplitude. That gives me 4. The minimum y would be midline minus amplitude, which would give me -2. So the overall range of this sine wave is going to go from -2 to 4. The period of sine or cosine is going to be 2 pi divided by w. Well, w is the number that multiplies to the x. So w is 2 for this trig function. So to see what my new period is after applying a horizontal stretch or shrink, I take 2 pi, divide it by 2. I get a new period of pi radians. So start to finish, it's going to take me pi radians to do one full cycle. Now, we go through the process and we like to quarter our period. And the reason why we want to quarter our period is because the percentage of the period in between our critical points of a sine or a cosine wave is a quarter of its period. So my critical points are maximums, midlines, and minimums. They're a quarter of a period apart from one another. So I quarter my period, I get pi over 4. Now we want to find our phase shift, because the phase shift is going to be our starting x value on our sketch. And so you set the inner part of the trig function equal to 0. So in this case, I'm going to set x minus 4 equal to 0. And I get x is equal to pi over 4. That's going to be my first point on my horizontal scale. Now technically my phase shift is because it's positive and went to the right. And so we're going to put all this on our graph. We're going to put on our vertical scale, we're going to put our midline, max y, minimum y. So max y 4, min y -2. Our midline was 1. Now on our horizontal scale, the first number that goes on our x-axis, or technically it's on our x-axis, the horizontal scale is going to be positive pi over 4. And then the number that we're going to add to that every time to get to the next number is a quarter of our period. So we're adding pi over 4 every single time to this number. And so my next number would be pi over 2. Then I'd have 3 pi over 4. Then I'd have pi. Then I'd have 5 pi over 4. So those are the values that go on my horizontal scale. Now when I graph, I like to take my midline and make a little dashed line here. So that way it's helpful for us to sketch and to kind of see where everything goes. Now the first point that we place on our graph, sine, starts at a midline. So the first point of sine goes on its midline. Now it's also positive. Now when we graph just y equals sine of x in a previous video, it started at a midline and then it progressed to go up towards maximum. So the first point here for sine goes on its midline. The next point would be a maximum. And then sine would come back to a midline. And then it would go to a minimum. And then it would go back to a midline. And then we connect the dots and showing the curvature of the function. And then remember, sine will continue on forever in both directions. And we have a graph of sine. Okay, now we're going to look at analyzing and sketching a cosine wave. And we'll start by finding the domain. The domain of any cosine wave is going to be the set of all real numbers. And then we're going to work to find our range. Well, to find our range, we need to find the amplitude and the midline. The amplitude you look at the number that multiplies to the trig function. In this case, -2 multiplies to the trig function, but that's not my amplitude because my amplitude is always positive. So our amplitude here would be +2. Midline is the number that adds subtracts on the end of the function. So midline is -3. Now we can find our maximum y and our minimum y. The maximum y, midline plus amplitude, that'd be 1. Minimum y would be midline minus amplitude, -5. So therefore my range of this cosine wave would go from -5 to +1. Now we go find our period. The period of sine or cosine can be found by taking 2 pi and dividing that by whatever w is. W is the number that multiplies to the x. So in this case, w is pi over 4. So my period would be 2 pi divided by pi over 4. And we do skip, change, flip, and that gives us 8. So start to finish is 8. We have 8 units. Now we're going to quarter that because that's the distance between our critical points. And so a quarter times 8 gives me 2. And we go find our phase shift. So phase shift, set the inside of the trig function equal to 0. And then we'll go solve for x. So that's going to give us, we'd have pi over 4x is equal to -pi/2. And then we go solve, and you wind up getting x is equal to -2. So now we're going to put all this on our graph. We'll start with our vertical scale. Our vertical scale, we get our vertical features. So our midline, maximum y, minimum y, I'll go on there. So we'd have 1, -3, and -5. On our horizontal scale, first number that goes on here is our phase shift, so -2. And then the next number, that we get, you take the quarter of your period and you add it to it to get to your next number. So I add 2, that takes me to 0, add 2 again, that takes me to 2, add 2 again, I got 4, and then I got 6. It takes 5 numbers on this horizontal scale to have a full period. All right, we'll put a dashed line for our midline. Now we're ready to graph. The first point that goes on our graph, well, cosine would start at a maximum because cosine of 0 is +1, our unit circle. However, I reflected this point by making it negative out front. So instead of a max, we're going to start at a minimum. So this cosine wave starts at a min, and then it would go to a midline, then it would go to a maximum, then it would come back to a midline, and then it would go to a minimum. And then we want to sketch that by and making sure we keep the behavior of the function the best we can. So I gotta have to show my curvatures around my points, and cosine will continue on. So there's our graph. All right, so now we're going to look at graphing the reciprocal function, so secant and cosecant. And in doing so, it's almost easier for us, in order to graph secant and cosecant, to graph their reciprocal functions first, and then once we get the picture of that, to turn them in to either secant or cosecant. And so starting here, y equals -1 plus 3 secant of pi over 2x minus pi over 2. If my goal is to graph it and then analyze it, I'm going to create a graph for the cosine wave that is the reciprocal of this. So I'm going to graph -1 plus 3 times cosine of pi over 2x minus pi over 2. Now, in order to graph that cosine wave, we'd find the amplitude, midline, and period of that function. You have an amplitude of 3, midline of -1, which means that our maximum y would be 2, because midline plus amplitude. Minimum y would be -4, midline minus amplitude. Then we go find our period, 2 pi divided by w, which gives me 4. And in my phase shift, set the inside equal to 0. Solve for x. That gives me a phase shift of 1, which is my starting point. And every other number that would go on my x-axis, I'd start with my phase shift, add a quarter my period. So my x-axis would go 1, 2, 3, 4. And then my vertical axis, I'm going to have my vertical scale numbers on it. So it'd go from 2 to negative 4, and I make sure my midline was present. Now, when graphing cosine starts at a maximum. It starts at a peak, but if it's positive out front here, it starts at a max. And so we'd have that cosine wave, and then I'd graph it. So I'd start here with my graph of cosine. Now to make secant, to change colors, secant here would be in purple. Everywhere cosine intersects its midline, secant's going to be undefined. So I put vertical asymptotes everywhere that cosine intersects its midline. All right, and then secant is going to share peaks with cosine. So everywhere cosine has a max or min, secant's going to share that point. And when sketching, cosine and secant turn away from each other. And secant's going to have that unbounded behavior. And so here in purple is the graph of secant. Now we can work on our analysis. So we're looking here at our analysis, and we can start with, well, where are the asymptotes going to be for cosine? Or not, excuse me, not for cosine. Where are the asymptotes going to be for secant? Well, we have vertical asymptotes, and I'm looking at the pattern that happens here. I have a vertical asymptote at 2, vertical asymptote at 4, and then so forth. And so the vertical asymptotes, so we have them at x equals 2, we have them at x equals 4. So if I wanted to write an equation that represented our vertical asymptotes, they would be at x equals, and it would be the set of all even numbers, which would be 2 times n, where n is an integer. Now let's look at our relative extrema. All right, where do I have relative maxes and mins? I have a relative max at 1, a relative min at 3, a relative max at 5, and I look at those numbers 1, 3, 5. That's a set of odd numbers, and so we have that max at x equals 1 and 3, and then we have that, or 1 and 5. And we have that min at x is equal to 3. And so if I wanted just to identify where extrema are going to be, extrema are going to happen at x equals the set of odd numbers, which would be, I can generate the set of odd numbers by saying 2n minus 1, where n is an integer. Right now, the range from the graph. Well, the range of secant is going to be the set of all real numbers except for this middle section here. So looking at this graph, it'd go from negative infinity to negative 4, and then it would go 2 to infinity. So our range, negative infinity to negative 4, inclusive on the negative 4, and then it would start back at y equals 2, and then increase forever, so 2 to infinity. And lastly, the domain. So the domain of secant is a set of all real numbers except for where cosine equals 0 or where I had those vertical asymptotes. So we would say, we already wrote an equation to represent where we have vertical asymptotes on all the even numbers for this particular function. So we say all real numbers except where x is equal to 2 times n, where n is an integer. And the last thing to do is to talk about what the period is. So start to finish of this wave here, we look, start to finish in between two peaks is 4 units. Now another way to get that is, remember the period of secant, just like the period of cosine, is 2 pi divided by w, where w is at pi over 2. So I could have 2 pi divided by pi over 2, skip, change, flip, start to finish 4 units. All right, now let's look at graphing a cosecant wave. And so we're given the function y equals negative 2 cosecant of 2 theta plus pi over 4 minus 2. Like we did for secant, it's to create a graph and analyze, it's often easier to look at its reciprocal function, which would be the same function but using sine. And so we go through, we create a graph of -2 times sine of 2 theta plus pi over 4 minus 2. And in doing that, we find the amplitude. The amplitude of the sine wave is 2. The midline of this sine wave is -2, which tells us that our maximum y would be 0 and our minimum y would be 4. We'd find the period of sine, 2 pi divided by w. 2 pi divided by 2 makes pi. And then we go find our phase shift where we set the inside equal to 0 and solve for theta. That gives us -pi/8. So on our horizontal scale, the first number we put on is -pi/8. And every number we put after that, we're going to add a quarter of our period to it. So that way we get a full, one full cycle. Our vertical scale are going to be our max y, min y, and our midline values for the sine wave. And then we'll go from there. So here I have the graph of the sine wave that we were just talking about. To create the graph of cosecant, everywhere that sine intersects its midline, cosecant will be undefined because that would technically make some kind of division by 0. So all of these midline points, I'm going to put vertical asymptotes for cosecant. And then after we do that, we have to remember that cosecant and sine will share peaks with one another. So they'll share the maxes and mins. And then kind of like with secant and cosine, cosecant and sine, they're going to turn away from one another. And cosecant will have that unbounded behavior as it approaches those vertical asymptotes. And we get our wave. All right, we had vertical asymptotes in this graph at -1 pi over 8, 3 pi over 8, 7 pi over 8. So what we would do is looking at that pattern of numbers, we're adding 4 pi over 8 every time. So we can say we'll have vertical asymptotes at x equals -pi over 8 plus 4 pi over 8n, where n is some integers. So we have a relative extrema at pi over 8, and then we have another one at 5 pi over 8. And I want to know where I would have extrema at. Well, we're looking at the pattern, the gap in between those radian values is pi over 2 or 4 pi over 8. And so we can generate an expression because all trig functions are going to repeat themselves over a certain interval of time. So we can just start with pi over 8. We know that we add, to get from one to the next, we're adding pi over 2 or 4 pi over 8. And that's the gap in between the intervals, so I can say pi over 2 times n, where n is some integer. Now let's talk about the range. So the range of cosecant would go from -infinity to -4, and then it would go from 4 to infinity. It's everywhere that sine is, that it doesn't share a point, cosecant will not have y values there. So our range, -infinity to -4, inclusive on the -4, union, and then 0 and larger. Because we'll have the domain of the set of all real numbers except for where we have vertical asymptotes. And so we'll say all reals except for x is equal to -pi over 8 plus, I'll simplify the 4 pi over 8, call that pi over 2n, where n is an integer. Okay, now we're going to look at graphing tangent and cotangent. And so up here above, I have the general form that kind of tells us how we'll go through the process of doing this. Now, we're not going to graph sine and cosine in order to make tangent. What we're going to do is we're going to look at this general form and identify where our points of inflections are. They happen at y equals 2. So my points of inflection are going to be at y equals 2. And then we know what our vertical stretch factor is. Our vertical stretch factor is 4. So I'm going to go to my vertical scale, and I'm automatically going to put 2 in the middle. And then I'm going to put, add 4 to it, makes 6, subtract 4 from it, and that makes -2. And then I'm going to put this right here on my graph. Now that's not much, but that's helpful because I know that everywhere I'm supposed to have that point of inflection is going to go on that line. Now what we do from here is we are going to find our phase shift. So I'm going to set the inside equal to 0. And so I got 2x minus pi over 6 is equal to 0. I solve for x. That gives me pi over 12. That's the first number that goes on the x-axis. And then we go find our period. Well, the period of tangent is pi over w. Well, w is the number that multiplies to the x, and so we get pi over 2. Now to graph tangent, we're also going to quarter our period like we did for the other 4 trig functions. So a quarter of the period is going to be pi over 8. So on my horizontal scale, the first number that goes on my x-axis is pi over 8. And then to get the next number, I add the first number is pi over 12. And to get the numbers after it, I keep adding pi over 8 to it. Okay, so we have our horizontal scale built. Now we have the tricky part, and that is to create the tangent wave. Now, the way you start this is you ask yourself, what is tangent of 0? On your unit circle, tangent of 0 is 0. So what that means is tangent starts at its point of inflection. Now we work our way and start to finish for tangent. So it's going to start, in this case, at a midline, or not a midline, a point of inflection. It's going to end at a point of inflection. And in the middle of this period is going to be its vertical asymptote. Now from its midline, when it goes, tangent's an increasing function if I don't reflect it from this point of inflection. As I go a quarter of my period, I get to apply my vertical stretch factor. And so this left-hand side of our graph will start at pi over 12 and will increase and start showing that unbounded behavior as we approach that vertical asymptote. On the right-hand side of that vertical asymptote, if I start at the point of inflection of 7 pi over 12, if I go halfway back to that vertical asymptote, I'll have to apply that vertical stretch factor. But so it'll be going down this time, and then I can get the other side of tangent. And so this is a window of 1 full period of tangent. So now let's talk about trying to figure out how we would describe where we would have points of inflection and where we would have our vertical asymptote. Well, to come up with the points of inflection, notice that we have a point of inflection at the beginning and the end of each period here. Now, we can start with pi over 12. And then the amount of space that happens in between pi over 12 and 7 pi over 12 is pi over 2. So we'll have a point of inflection every pi over 2 times n, where n is an integer. We'll have a vertical asymptote at pi over 3, and then the next vertical asymptote we would have would be when we go 1 full cycle to the right of that, which would be if I added my period to it. So pi over 3 plus pi over 2 times n will be the set of all vertical asymptotes. So x is equal to pi over 3 plus the number of times you want me to apply my period. So it'd be plus pi over 2 times n, where n is an integer. Now the range of tangent, even though you don't really see it very well here, it's the set of all real numbers, because it's going to decrease forever here. It comes up to its point of inflection, and then at the point of inflection it will continue to increase forever. So the range is all real numbers. The domain of tangent is the set of all real numbers except for the vertical asymptote. So we say all reals except for when x is equal to the vertical asymptote, which we already wrote in an expression for that. So x is equal to pi over 3 plus pi over 2 times n. All right, so now we'll do the same thing for a cotangent function. It's the last function left in our video out of our 6 trig functions. Now, like we did for tangent, I'm not going to create the graph of cotangent by graphing sine and cosine. Instead, I'm going to use its key features. I know that cotangent is going to have points of inflections at when y is equal to -2. And then the vertical stretch factor is 3. So on my vertical scale, I'm going to have y equals -2. And then I'm going to add and subtract 3 from it. So I'll have y equals 1 and then y equals -5 on there. To get our horizontal numbers, we figure out what makes the inside equal to 0. So I set the inside equal to 0, solve for x. We get x is equal to -3. That's our phase shift, or our starting x value. To get the other points that go on the x-axis, or the x scale, we find our period. So pi divided by w, w is pi over 8. So we get a period of 8, and then we quarter that to get the spacing right for our horizontal scale. So we quartered 8, we get 2. So on our x-axis, we'd have -3 to start with, and we keep adding 2 until we get 5 points to put on there. And we do that, and so we have our scale set here. And now we're ready to start creating our sketch. Well, to figure out what we start at, what happens at -3? Well, you figure out -3 would make the inside of cotangent equal to 0. On your unit circle, cotangent of 0 being cosine divided by sine is undefined. And its cotangent starts at a vertical asymptote. And then it's going to end at a vertical asymptote. In the middle, it's going to have its point of inflection. And then if you remember, cotangent's a decreasing function on its domain. So halfway in between the vertical asymptote and the point of inflection, we're going to apply our vertical stretch to make sure that this cotangent function, which is not reflected because there's no negative sign in front of the x or in front of the cotangent function, make sure it stays decreasing. And then we'll sketch what our behavior that goes through there, and we get our cotangent wave or cotangent curve. Now we'll finish our analysis. And so we've already found the period. And so where do we have our points of inflection? All right, well, we have a point of inflection at x is equal to 1. And now when would the next one happen? Well, the next one would happen one full period away from that point to either the right or the left. And we've already figured out that our period is 8 units. So we can write an equation to represent that. Our points of inflection would be at x is equal to 1 plus our period times n, so 8n, where n is an integer. We have vertical asymptotes at -3 and 5. So I'll write those two. We have vertical asymptotes at x is equal to -3 and x is equal to +5. You see what the gap in between those two are. It's 8 units as well. So we can write an equation that we'll have vertical asymptotes at x is equal to -3 plus 8n, where n is an integer. The range of cotangent is all real numbers. And now the domain. The domain of cotangent is going to be all reals except for where it's undefined at, which are at those vertical asymptotes. So we'll say all reals except. Now we have the expression that represents our vertical asymptote, so we'll say except where x is equal to -3 plus 8n, where n is an integer.